Um, so we resume with the simple harmonic motion. Simple harmonic motion. Mm, and need to be aware of the fact that it's an oscillatory motion and it can also be conjugated with additional mechanisms. For example, here's a wave. This object, the wave for motion. This Excuse me, I have to change my pen. Simple harmonic motion. The waveform is something like this, and the mass which is moving up and down can also be attached to a spring system where there is this restriction. And now we have the spring constant K here. I will show you in a bit. So we have this XY plane. This is the wave, and the mass is attached also with the spring system. So the first thing is F is equal to ma, the Newton's law, and the second thing is F is equal to minus kx. Yes, the spring constant and the displacement. The spring has a constant x and it has a displacement usually between the intervals. Uh, well, actually this varies, but in general this is vertical. Uh, X, spring constant K. So minus kx is the force in the mass spring system. We can equate the two. Ma is equal to minus kx, which means that A is equal to minus kx by m, and A is equal to minus k by m dot x 3. And we also know from mechanics that square of the angular velocity is basically equal to k by m. So minus omega square would be minus k by m. So we can equate now, or we can rather substitute in the form for A, which says A is equal to minus omega square x, rather omega square x, because the minus sign cancels out. Okay, so in this situation, and so we get back to this equation which says omega square is equal to k by m, yes, omega is equal to k by m under the root, and omega also is equal to 2 pi by t. Angular velocity is 2 pi by the time period. This is known. So now we have the situation where t can be formed. T is equal to 2 pi by omega, and in this form we can put the substitution of omega. So t becomes 2 pi by k by m under the root. Okay, and as f is equal to 1 by t, so f will become 1 by 2 pi by k by m under the root. Yes, in this situation f would become k by m under the root by 2 pi. So this is the form for the time frequency and the time period of simple harmonic motion. It depends much on the angular velocity and its substitutions. But we should also know the relationship between acceleration, displacement, and angular velocity, which is equation 4 here. And now we have a form for circular motion, which we will develop circular motion as simple harmonic motion. Circular motion as harmonic because the repeated cycles make it harmonic. And so this circle is important to notice here. This is the radius of the circle, the xy plane, x and y, which is something like this, xy plane for instance, and the angle and the centripetal acceleration because it is directed towards the center. So centripetal acceleration AC is directed towards the center. Center is here. AC is equal to v square by r in magnitude, or in this case v naught square by r, and v naught is r omega, the relationship between linear angular velocity. And so AC is r square omega square by r, which means that AC is r omega square. Now it has components. You see, AC is directed towards the center, AC, but it has components. Let's say we make a projection and ACX is here, and then ACY would be somewhere around here. Yes, ACY, the vertical component of the centripetal acceleration. So this dimension in general would be x, and this vertical projection would be y. And now we remove the xy plane, so ACX would be r omega square cos theta, and cos theta here would be x by r base by hypotenuse, and sine theta would be y by r. So if we are to substitute the cos theta, so ACX will become r omega square x by r. So ACX, the x component of centripetal acceleration, is very much omega square x, which is the standard form of acceleration in harmonic motion. Okay, so this is of interest. Highlight it, rather mark it, and if we look into the sign conventions, for example, we start off with a c to be negative, then here with the sign convention, this could be omega squared x with minus, which is sign convention. And for proportion, we can write this directly proportional to negative x. The ACX is directly proportional to negative x if we are to make a proportion. Okay, but in general, for magnitude, this is the form: AC is equal to omega squared x, and this is it. We can also do the estimation for, let's say, the vertical component. ACY is equal to r omega square sine theta, and sine theta, as we know from the approximation, is y by r. So ACY is equal to r omega square y by r. So ACY would be omega square y, and if we introduce the sign convention, ACY would be minus omega square y, for the sign convention, because this is the magnitude, and if we are to put the direction, we put put a sign of minus here, but we didn't because of the magnitude. So sign convention here, and ACY is equal to AC is directly proportional to minus y if we make it a proportion. Yes, this is also worth noticing. Yes. So to resume with the period of simple harmonic motion, S is equal to V naught t. Initial velocity into time gives us the distance or the arc in case of a curve, and S is equal to 2 pi r, which is the circumference of the circle. We can equate the two, 1 and 2. 2 pi r is equal to V naught t. So t would be 2 pi r by V naught, and V naught is our omega, as V is our omega. Okay, so wait, V is our omega, which is denoted by a V naught here. So T would be 2 pi r by r omega. So T would become 2 pi by omega. So this is the time period, and for frequency we will reciprocate, or make the reciprocal. F is equal to 1 by t. So F is equal to omega by 2 pi. So this also is significant. And for displacement, we notice a little bit of a thing for displacement, making slight adjustments. Yes, so for displacement, we need to keep this arc, this radius, this angle, and the projections in mind, x here and y here. Yes, so as cos theta is equal to x by r, so x is equal to r cos theta. Yes, understandable. And as we know that x is equal to r cos theta 1, and we know that theta is equal to uh, omega, as we know, is equal to theta by t. So for theta we have omega dot t. Yes, so now we substitute this omega dot t in place of theta, so x becomes r cos omega t. Now we have the displacement in terms of radius and the cosine component of the product of angular velocity omega and time period t. Okay, not to complicate things, but this can also be thought of as see, sine theta is equal to y by r. So y is equal to r sine theta. Okay, or we remove it from here and put it here. Now y is equal to r sine theta in terms of vertical component. Theta is equal to omega t, so y is equal to r sine omega t. Okay, so number 3 here significant, and also number 4 here if somebody is comfortable with approximating on the vertical axis. And for velocity, you see, we need to keep in mind that, you see here, the x component of velocity would be v naught cos of theta, and y component of velocity would be v naught sine theta. No, actually v naught x and v naught y. Okay, so v is very much v naught sine theta. Why so? There must be a rationale behind it. I cannot go into the details right now. We can explain that in some other visual. But the tangential nature of velocity, for example, see here, is to be one of the major factors why we take the significant vertical component. Okay, so we'll see, we'll look into it later on, but right now we are trying to develop a form. So as we know that v naught in our case is the initial velocity is equal to r omega, so we put the value of r naught with the form of v naught into the main thing here, 1 here, v is equal to r omega sine theta. Okay, and also we know that sine square theta plus cos square theta is equal to 1 in trigonometry. So this is, let's say, 2 here, so sine square theta is equal to 1 minus cos square theta, and sine theta is equal to 1 minus cos square theta under the root. So we can use this as substitution. Let's call it a. Okay, let's call it, yes, a, and instead of s we just put a. S can be confusing. So and also another substitution, as we know that cos theta is equal to x by r, so sine theta is equal to 1 minus x square by r square under the root. So in general, I mean, I would be comfortable writing v is equal to r omega 1 minus x square by r square under the root as a as a main mathematical form for velocity, which is predominantly the vertical component here, but the significant one. And then we can go on with the solutions, and we can also do this stuff. R omega is equal to r square minus x square by r square under the root. R comes out of the root and gets cancelled out with the r outside, so v is equal to omega into r square minus x square under the root, and v is very much equal to omega into r plus x into r minus x under the root. Yes, this is from mathematics. R is the radius, x is the displacement, and omega is the angular velocity, and v is the linear velocity. So this is very much it for the basic parameters of simple harmonic motion, and I hope it is understandable for the students. And now we get back to simple pendulum for a bit, because we have to do a little bit of work in that area. We have to do a little bit of work in the area in the domain of simple pendulum, because we only introduced it previously. So for a simple pendulum, we make a figure. A figure says mass suspended by a string, and then it moves, makes an angle theta. L is the length of the cord, and x is the displacement here. So the components of velocity basically depend on weight. So here's the x component of weight, and here's the y component of weight. Wx is equal to mg cos theta. Okay, let's not write it here, we'll write it on the